Welcome everyone. Today I'll be presenting data parallel actors, a programming model for scalable query serving systems. This is not your typical research paper. Um, I'll first talk about the motivation for this paper. Like uh, there's a proliferation of query serving systems for specialized workloads out there, the Druid, the Spino, the Solar, and the claim of the paper is that all of them are running on like have almost the same features with regards to distributed systems. So I've gotten a bit ahead of myself. I'll first go through my presentation. Like, let's first answer the question, what are query serving systems? This was a new term for me because for me, everything was just a database or a data store which stores and gets your data. So query serving systems, they need low latency data parallel queries. They need frequent bulk data updates. Examples out there are Apache Druid, Elasticsearch, InfluxDB, etc. Their workloads run at a very large scale, and like developers must implement complex distributed functionality in them, like data replication, update consistency, fault tolerance, uh, and load balancing. So the claim of the paper is again that the distributed functionality varies very little between these query serving system, but is implemented in a custom fashion in each of them. And since all of these systems are proliferating for every use case out there, it might be better to do something about it. Now, why is there custom code written? Like, because scaling these systems is very hard. Like you need to handle your failures, you need to ensure data consistency. These distribution layers that everyone has written, they are a bit difficult to implement uh, because distributed systems are hard. So just this layer is about 70K lines into it. So when you have so much code like this, like adding new user requested features becomes quite complicated for you. These days we have elasticity in cloud environments, but none of the query serving systems exactly support elasticity. Neither do they support load balancing. So yeah, coming back to their major insight that all the distribution layers are similar, and if they are similar, can we make it easier to build such systems since they are difficult to build? So the answer to this question is their data programming actor model, uh, abbreviated as DPA, which runs on their Uniserve runtime. Uh, the core proposition of DPA is that you can construct a distributed query serving system from purely a single node system. You just have to think in the context of a single node. So this sort of separates out responsibilities in that system. The runtime Uniserve takes care of distribution and scalability, uh, and it automatically provides other distributed features like fault tolerance, consistency, load balancing. While the developers are only responsible for the core unique functionality of the system, which is storing data and querying data. So because this distribution layer has been abstracted out, new features can be added to the Uniserve layer with very minimal modifications to the core of the system, which is storing and querying data. So how exactly can a developer write a DPA application? Like they need to write an actor implementation. We'll see what they need to do for that, the interface for that, and they need to write a query planner. So coming to the basic component of DPA, which is an actor, like an actor interface has create, destroy, serialize, deserialize methods. These are the four core methods that every actor has to implement. The snapshot method is optional. If and like an actor in this programming model, it encapsulates an opaque partition of data. So they take an example of a leucine inverted index. So an actor is encapsulating that leucine index, and this data set, like whatever data set you have, it is partitioned across many actors using partition keys, so that all records inserted with the same key are assigned to the same actor. Uh, the difference they have from traditional actors is that DPA can only communicate via these APIs, and they cannot just pass any arbitrary messages. Everything else, like keeping their state, keeping their internal state, uh, is like the traditional actors. Now, how does the DPA model support updates? For that, there are like another set of interfaces that the developer needs to implement, and like they have parallel update functions, which update multiple actors in a single table. And to perform updates, devs implement an update function with these methods. So if you see here, the consistency level is configurable. It is upon you, uh, as well as the atomic guarantees for your updates. So the eventual consistency is provided by default. Uh, you only need to implement the update method for that. For stronger guarantees, you will need to implement the participant protocol of two-phase commit, which is prepare, commit, and abort. And how do you like execute parallel queries over data which has been stored in many actors? So to enable these queries, DPA provides these general set of parallel operators, which lets developers construct queries from these generic operations like map, scatter, gather, query, and combine. So like devs, as I mentioned earlier, also have to implement a query planner in this systems that translates their queries to the set of abstractions that have been created by DPA. Uh, all of these operators that we see right now, they cannot modify the data. They can only materialize output, and this output can in turn be used by other actors as well. So this is very useful for the scatter gather phase, for retrieve and combine. Let's first look at the map operator for querying, like which is a simple transformation which is applied to several actors in parallel, and then it materializes the transform data for you. An example can be an operator which searches for documents uh, in a data set based on a particular field. The next operators that we have, which are retrieve and combine operators. Retrieve computes values from actors in parallel, and then the combine operation combines all of those retrieve operations into one value. They are typically the last two actors executed in any query. The next ones are scatter and gather operators. They enable collective operations, and they provide data communication between these actors. So they enable operations like broadcast and shuffle. Like a gather operation computes pairs of data from actors. A scatter operation combines data with the same attribute and materializes a result. So like this is the core of the DPA programming model, which developers have to understand and have to implement their data systems in, so that like Uniserve can do the magic of distributing uh, and can like execute queries at scale. This brings us to the heart of the paper, which is the Uniserve runtime model. Let's look at its architecture. So a Uniserve cluster consists of many data servers, and each server runs a thin Uniserve layer over the developer provided code that uh, we have just seen. And clients send queries and updates to the server. Each client also runs a thin Uniserve layer, which is over the developer provided query planner. Uh, all of this is managed by one single central coordinator, which manages state with the help of Zookeeper. It is responsible for distributed capabilities like load balancing, failure recovery, and elasticity. Uh, Uniserve can also backup data to an external durable storage system like S3 HDFS for fault tolerance. The server layer in this actually facilitates query execution. It receives query operators and updates from clients. Devs have already written the mapping from their query to the Uniserve operators. So the servers receive those, and then they execute them in the underlying system using the DPA interface. Um, Clients also plan their queries and submit them to the appropriate servers. So they learn the locations of all the servers where their data is stored through the central coordinator, which relies on Zookeeper. So let's move to how Uniserve gives us update, consistency, and atomicity that it promises. So, like I said, eventual consistency is like the default level here. You just implement the update method. Those updates are synchronously applied to the primary actor for that data, and then it is replicated to secondaries, and all updates are applied in order. Why they have made these guarantees configurable is because every system out there, uh, like their data consistency guarantees vary depending on what sort of use case they are solving. Uh, so with that, like if you want serializable updates, you need to implement the two-phase protocol, and your update is only applied if Uniserve is able to successfully prepare a phase on all actors and its replicas. There was another method that we had seen, which was optional, snapshot, that is used for providing full serializability. So you implement the update functions as well as the snapshot method, and Uniserve will create a version copy of each actor's data upon update, and ensure that read queries see consistent data versions across actors. All throughout this, like Uniserve makes certain assumptions. Since we'll be talking about fault tolerance and failure recovery next, I thought it'd be better if we go through those assumptions first. Like Uniserve assumes that servers will fail only by crashing, and those crashed servers will remain crashed until we restart them. And if we restart them, they're actually a new server. uh, Coordinator and Zookeeper, which is like the heart of Uniserve, they are always available. If either the coordinator or Zookeeper fails, the cluster will be unavailable until it is restarted. So the coordinator stores all its state in Zookeeper. If Zookeeper is also down, then the system is also unavailable. With that, let's look at how Uniserve does fault tolerance and fault failure recovery. It provides update durability via replication and asynchronous backup to durable storage like S3. Uh, you Data loss is only there if all the replicas of an actor fail. And even if they fail, all data committed since the last backup to durable storage is what you lose. Update fault tolerance. Like Uniserve ensures that all replicas of an actor converge to the same state. So it's possible for an update to partially succeed. Say on some of the replicas, the replicas crash. So the update is only on some actors, and at this point, the coordinator chooses the replica with the most advanced update as the new primary. For serializability, updates totally succeed or abort on all the replicas. So the clients write any commit decision to Zookeeper so that everyone is always in a consistent state, and the server can reference Zookeeper state if the client fails. So till now, this is stuff which we have almost read everywhere, and next is the two new things which Uniserve was seeking to solve, like adding features like load balancing. How do they do that, and elasticity. So first, let's look at load balancing. Uniserve does load balancing through data placement. It it manages the actor to server assignment, and it uses the greedy load balancing algorithm for that. So it moves most loaded actors from most loaded servers to least loaded servers, and it replicates actors whose load exceeds the average server load. So this is also configurable. You can define your data placement policy, and how actors are moved during load balancing. Data is fetched from durable storage first, and actor is started on the target server. And then uh, this replica syncs with the primary, and then the clients are notified that some actors have moved, and if necessary, the original copies of actors are deleted thereafter. In this case, sometimes it may happen that a primary is removed, so updates can block for a brief period while a new primary is designated. Uh, this feature is necessary for consistent performance across all workloads. Uh, since the load on the system can vary over time, they benefit from elasticity, which is the ability to dynamically adjust the cluster size. So this is also configurable, and utilization is based on the same auto scaling algorithm that the cloud services use. You add server if CPU exceeds an upper threshold, and remove server if it comes below a threshold. With this, we come to an end for Uniserve runtime. So the goal of the paper was that they would define these new abstractions, and these abstractions would have similar performance as to what the current systems have. So for this, they've evaluated four systems. They have ported them to DPA, and their setup is a cluster of M5D.xlarge AWS boxes with 4 CPUs, 16 GB of RAM. So in this evaluation, they look at throughput, and we're going to also look at load balancing and elasticity. So this first benchmark is for throughput versus latency for the system's native distribution layer and their DPA ports on uniform workloads. And each benchmark is run with several workers who repeatedly query the system and wait for it to complete. In this, we see that DPA ports perform similarly to the native systems. The next benchmark is the scalability benchmark, which is also on a uniform workload. And as we see, like as the number of servers scale up, the performance is near constant. The next benchmark is the TPCH benchmark on 4 cores on a single node, which is the first figure. In this, we see Uniserv is mostly competitive with the native ones. This can be due to the fact of the communication cost during the scatter and gather phase that Uniserv has. On 160 cores, Uniserv easily outperforms Spark and matches that of Redshift. The next benchmark is for the update performance. Bulk writes are used here since they are what typically happen in subsystems. For Solar and Druid, eventual consistency has been provided, while for MongoDB, serializability has been enabled via two-phase commit. Here also, Uniserv matches native system performance. Now, this benchmark demonstrates the load balancing feature, and here Uniserv is compared against Druid, because Druid has a load balancer as well. So Druid's load balancer ensures that each server hosts the same amount of data, but does not balance query load. So the first workload, which is the left figure, it varies the queries sent to a single slice of data. So 7 out of 8 queries are sent to one single slice of data. But since Uniserv balances load for such kind of hotspot due to its greedy algorithm, it outperforms Druid by almost 3x. The right side figure is the second workload, where the fraction of queries sent to the hotspot are varied. Due to again load balancing, Uniserv's performance is near constant, but Druid's latency increases as the fraction of queries are increasing. The next benchmark is the elasticity benchmark. Like, as the servers are added, how does Uniserv perform? The benchmark was run for 6 hours by them, and the target throughput was varied. All queries are uniformly distributed over a minute. Uniserv's latency spikes for a bit when it adds a server. If we observe all the peaks in the fourth graph, apart from this, if we see Uniserv is mostly able to scale to meet the target throughput. The latency spikes very little and only happen when, like, Uniserv is notifying everyone of the new server, like we saw in the fault tolerance phase. The next graph, like, it shows us how Uniserv deals with failures. 3 minutes into the benchmark, they killed a data server and saw how the system reacted. So the left one is for a single node, single replica. When the server gets killed here, both systems take some time to recover by restoring replicas from durable cloud storage. The right one is has 4 replicas of both Druid and Uniserv. So when a server is killed, like, Druid fails quite a lot of queries and takes time to get back up to route queries to the replicas. However, Uniserv recovers almost instantly. With that, the evaluation ends. The limitations of the system, according to them, are that they assume queries are data parallel. They assume that systems are specialized for low latency and low write concurrency. With that, we come to the end of my presentation. Thank you.
Yay! Awesome, Akash. That's a very detailed presentation. Yeah. Thanks a lot.
Thank you.
Yeah.
We are still recording.
Oh,